Today we're going to talk about a weather balloon example. In our question, a weather balloon is released from rest at the ground level. The mass of the balloon, the mass of helium inside the balloon, the volume of this balloon, and the two densities and T values are given. And we have to assume the balloon does not burst and air resistance is negligible. First, we have to find the upthrust acting on the balloon at the ground level. So first, let's make a sketch. Okay, here is the weather balloon, and helium is inside here. And we need to find the upthrust. So we have a formula for upthrust, which is U is equal to upthrust, which is equal to rho Vt. And here, rho is the density of the surrounding fluid. So here the balloon is floating in the air, so we have to consider the density of air. Okay, so we can just plug in the values. Density of air is 1.23 kilogram per meter cube, and the volume is 2 meter cube, and T is 9.81. And if we plug in the number, we'll get 24.1 Newton. Okay, we're done with the first one. Let's go to the next one. Determine the initial acceleration of balloon just after release. So to find the initial acceleration, we have Newton's second law, which is the net force is equal to ma. We know the mass of the balloon and the mass of helium inside the balloon. We need to find the net force. So in our case, there's the upthrust acting on the balloon, and this balloon has weight, and we're ignoring air resistance. So only these two forces. So here, we need to know the quantity of these two forces. We have the upthrust, so we need to find the weight. So W is equal to mg, and here m is the mass of the helium gas and the mass of balloon. The mass of helium is 0.4 and the mass of the equipment is 1.2. And here we'll get around 15.7 Newton. Okay, so we know the upthrust is greater than weight. That means there will be the net upwards force. Which will be equal to the upward upthrust minus W. And then for this one, we will get 8.4 Newton. Okay, now we have the net force. Oh, we need to find the mass. So the mass is the mass of helium plus the mass of the equipment, which is 0.4 plus 1.2, which is just 1.6 kilogram. Okay, now we can use Newton's second law to calculate the initial acceleration of this balloon. And here, the force is the net upward force. So for this one, we'll get 5.25 meter per second square. Okay, we're done. So let's move to the last part. It say as the balloon rises, oh sorry, this should be C. As the balloon rises, the surrounding air density decreases. Explain the motion of the balloon as it reaches constant velocity and then maximum height. We have to assume the volume of this balloon and T value, it remains the same. Okay, so it is given as the balloon rises, the air density decreases. So in our given quantities, we have, in this problem, we have the upthrust. So upthrust is rho air Vt. So as the air density decreases, that means the upthrust decreases. However, W remains the same because the mass of the helium and the balloon equipment, it remains the same and T values remain the same. So W remains the same. And our equation for the net upward force, it is U minus W. So as U decreases, the net upward force decreases. And then at one point, there will be like, as W remains the same and U decreases, there will be a point where upthrust is equal to weight. So at that point, there will be no net force. That means, according to Newton's second law, F is equal to ma. Then at that point, as long as there is no net force, there is no net acceleration. So when the balloon reaches this point, the balloon will continue to go up with the constant velocity. All right, this part is done, and we have to discuss a little more. So as as the upthrust decreased more and more, at a certain height, there will be a place like W is greater than the upthrust. So let's sketch a little bit. The upthrust is acting on the balloon and is in the upward direction, and the weight is acting in the downward direction. So at that point, there will only be the net downward force. That means, according to Newton's second law, again, there will be the net downwards acceleration. So our velocity decreases. And then it will reach 0. So at that point, the balloon will come to a brief stop. So that means at that point, the balloon reaches the maximum height. And our question ends here. In real life, because of this, the velocity of this balloon can continue to decrease. It might become negative and the balloon will come down again, but the question stops here. Okay, that's all for today. Thanks for watching and see you next time.